Today, you're all here to learn about graph databases. I'm not going to go real in-depth about how to set up a graph database, how to configure it. The documentation for the graph database I'm going to talk about, Neo4j, is amazing. They do a really good job about that. My goal here is more to talk about what a graph database is, why you should care, and what some of the use cases for them are, and how you can start kind of envisioning your own application domains in a graph-like fashion to start utilizing this really cool technology. So, first thing, I'm Josh Adell, that's my Twitter handle. I work for a startup in Durham, North Carolina called Service Trade. We're a small 9-person team. Unfortunately, we are not using graph databases, but we will hopefully one day once I get permission to refactor a bunch of our code. Every now and then, I write on my blog, everymansoftware.com, talking about PHP, software development in general, Agile, things like that. I'm the author of Neo4j PHP, which is the PHP library for talking to the Neo4j database over REST, over HTTP. And down there, I've put a link to Joined In, if no other speaker has mentioned that yet. Every talk at the conference is up on Joined In. Joined In is the site for giving speakers feedback on their talks, on how they did as presenters. So at the end, I'll put that link back up, and please go there and give me feedback so that I can learn as a presenter and make this presentation better for other people. So first, I want to take a quick poll. Raise your hand if you had ever heard of graph databases before you read the synopsis for this talk. Awesome, very cool. Raise your hand if you are currently using a graph database in a production environment. I've never had anyone raise their hand to that question, which is unfortunate because graph databases, as we're going to see, are really cool and they're really applicable in a lot of different use cases. So let's start by talking about a problem.
Oh, he's the solution.
He is the solution, well, he's part of the solution. But the problem we're trying to solve is that Kevin Bacon has been in too many movies with too many other actors. He's been in so many movies with so many other actors that there's become a game named after him. Who here has heard about the
6 Degrees of Kevin Bacon?
The 6 Degrees of Kevin Bacon, exactly. The basic idea of the game is that given some actor or actress, find a chain of movies that that actor has been in with another actor who's been in another movie, with another actor who has been in another movie with Kevin Bacon. And whoever comes up with the shortest chain wins. This is actually kind of a specific case of a much more general type of problem called an arbitrary path query. You hear that a lot in graph theory. Arbitrary path query means given some entity that is connected to some other entities, find me a path from that first entity to a second entity through their connections. This is the basic unit of social networking. So if you think of Facebook, if I am friends with somebody who's friends with you, you are a friend of a friend. If you have another friend, I am a friend of a friend of a friend, and so on and so forth. Facebook, LinkedIn, they all work this way. So we're going to talk a little bit first about a typical way you might try and solve this using a relational database like MySQL. We've all used MySQL in production. We all know how it works. Lots of developers know how it works. And as a first stab, we're going to try and play the Kevin Bacon game using MySQL. So I'm using subselects here. If subselects make your head hurt, convert them to joins, but the basic process is the same. The first thing we need to do is find all the actors who have been in a movie where that movie is in the set of movies that Kevin Bacon has been in. So that would be a 1-degree separation. This actor has been in a movie with Kevin Bacon. If the actor we're looking for has been in that set, great, we win. But let's suppose they're not. Now we have to go a 2nd degree out. We have to find all the movies that that actor has been in. Then we have to find all the actors who have been in those movies. Then we have to find all the movies they've been in. And then we have to see if Kevin Bacon is in that set. And if we do, that's a 2nd degree connection. We win. The game is called 6 Degrees of Kevin Bacon, so they might not be in that second degree. Now we have to go to a third degree. All the actors in all those movies, all the actors in those movies, all the actors in those movies, all the movies they've been in, and then Kevin Bacon. As you can see, this query just gets uglier and uglier and uglier. So this is just the third degree, but you can imagine how ugly a 6th degree find would be. This is a bad deal. This isn't performant. It's not easy to grok. You can't understand it just by looking at it. You really have to try. If I didn't have third degree there, could you tell me at a glance how many degrees deep that was actually searching? Probably not without reading it really carefully. So this gets us at a fundamental truth. Relational databases do not handle relationships. It's unfortunate that they're named that because it's just true. Relational databases are actually based around set math, computer science term. Basically means, given some criteria, find me all the entities in a big bucket of entities that are in the set that match that criteria. And if you need to join that with another set, you're doing basically an intersect, a set intersect, a Venn diagram, or a union, or some such like that. This isn't really good for that arbitrary path query problem we were talking about. It's certainly not arbitrary. You can't just say, no matter how deep the relationship is, just keep going until you find it. You have to be very specific. First, find me at the 1st degree. Then find me at the 2nd degree. Then find me at the 3rd degree. So it's not arbitrary, and it's not really even path related either. So people recognized this problem and they said, SQL is dead, long live NoSQL. Here are all these NoSQL databases that avoid things like schema lock-in or drop transactionality because nobody cares if data actually lives or dies anywhere. And the unfortunate thing is that while these databases are slightly more intuitive in dealing with different types of data, none of them, or all of them, have the same flaw that relational databases do, which is that relationships between pieces of data aren't first-class citizens. They're not fundamental to the way the data is structured. A disparate document in Mongo is not related to another disparate document in Mongo. You still have to do a join somewhere. It's just now, instead of having a relational database that has a nice join syntax, you have to bring both of those things up into your application level and join them in the application code. So we haven't actually solved the problem we're trying to solve. Enter Neo4j. Neo4j is a graph database. Graph databases are made to solve these specific types of problems. Not necessarily find me all the set of things that match criteria, but find me how those things are related to each other. Find me if they are related or not. Neo4j is pretty awesome. It's the most popular of the graph databases. It's been around for about 11 or 12 years now. It's got a large community support. It supports transactions. It's ACID compliant. Comes in different modes. You can either run it embedded inside of a Java program. It is a Java application. Or in the past couple of years, they came out with a REST server, which we'll talk a little bit about, but that's how PHP can talk to it. And it pretty much has bindings for every language, every mainstream language, and a couple not so mainstream languages. So a little more in-depth about graph. Computer sciencey term, a graph is nothing more than an ordered pair of a set of vertices and a set of edges, where each edge is nothing more than a pair of vertices. If the vertices in the edges are in a specific order, in other words, the edge A to B is not equivalent to the edge B to A, then we call that graph a directed graph. And if you think about this, you can think about a flow of water down a stream, branching off into different rivers and things. Each branch is a new node with a new relationship coming off, and because the water only flows in one direction, that river and all its streams are a directed graph. I'm going to change up the vocabulary a little bit. The precise computer science graph theory vocabulary is vertices and edges. Instead, we're going to talk about nodes and relationships, because that's what Neo4j uses. Neo4j is a specific type of graph called a property graph. In a property graph, you have nodes which have properties and labels. Properties is basically just a key value pairing. It's a hash. And labels, you can think of them like a type. So person is a label. This node represents person. Presenter is a label. This node is a presenter. Nodes can have multiple labels. So this node is a person and a presenter, or a person and a conference attendee. Relationships are first-class citizens in a database, in a graph database. They can also have properties. So every relationship between two nodes has properties of its own. It has a specific type, which is kind of like a label for the relationship, except a relationship can only have one type. And in a property graph, relationships always have a direction. So a relationship from A to B is a different relationship than a relationship from B to A. And you can have a relationship from A to B and B to A, each that have the same type, but different properties, or different types and the same properties. It doesn't matter. Nodes and relationships are basically bags of properties, where a relationship has two additional properties, the start node and the end node. Think of them that way. Then there are other useful constructs like indexes to allow you to query. So I want to find specific nodes where the name property of that node equals something or is a regex containing something. And then in Neo4j 2.0, they introduced things like unique constraints. So when you're inserting or updating nodes, you can make sure that you're not creating duplicate nodes and relationships. Everyone cool so far?
Yeah.
Awesome. So using this property graph, we can describe pretty much any system. And every system can pretty much be described as a graph. So a graph, that's just kind of a weird abstract little thing, but something you can think of like a network that has multiple servers, or maybe it's partially a mobile network, so it has cell phone towers and then specific phones that are attached to it. That's a graph, where each thing on the network is a node, and the connections between them are the wired or wireless relationships between those nodes. Social networking, of course, we talked about, friends of friends of friends. But even something like a map, like Google Maps, is a giant graph. If you look really closely at this, everywhere where two streets intersect is a node. And every street between two intersections is a relationship between those two nodes. So one use case for a graph database could be find me a path from my starting point to my ending point. And at that point, you're using very simple graph query constructs, pathfinding, just like playing the Kevin Bacon game or doing social networking. And there are tons and tons more use cases for graph databases. There are white papers written about people using graph databases, Neo4j and others, to do things like manufacturing, supply chain management. Banks and insurance companies use them to detect fraud. I was at a conference where I was listening to a guy who works for a game company in the UK, and it's an online poker site, and they use graph databases to detect people who are trying to game their referral system. Bioinformatics, medicine, geospatial stuff that's more high-level abstract, like natural language processing. All of these things can be broken down into basic relationships between nodes. Your relational database is a graph. If you use foreign keys, or even if they're not official, the foreign key construct, if you have a column that is this ID maps to the primary key in another table, you've made a graph. If you match up all those foreign key relationships and then extend them out, it's nothing more than nodes with relationships between them. That big gray arrow in the middle, that's an ORM. How many people use an ORM of some kind? A couple of you? All your ORM is doing for you is taking a relational database and transforming it into an object graph in memory. So that's an interesting question then. Why can't we just treat our relational database as a graph? Well, some do. If you've ever heard of FlockDB by Twitter, all that is a layer that sits on top of MySQL that allows them to query MySQL as a graph. But at the end of the day, that's still not going to be as performant as natural graph processing because the data is still stored in a relational way instead of in a graph-like way. So as you start to get more and more into graphs and graph databases, you start to realize everything can be modeled as a graph, pretty much. Even stuff that looks on the surface like it's very, very tabular. If you think of something like airline schedules, if you flew in, or train schedules, or bus schedules, it's very tabular layouts. But if you think about it, there's an underlying graph there. This vehicle is going to be at this stop at this time, and then it's going to take a path from stop to stop to stop. You are all attending a conference. I'm sure there's a big list of all the conference attendees that looks like a list, looks like a table, but if you think about it, this conference is an entity. You all have an attended relationship with the conference. I call this the Zen of Graph Databases. Everything is a graph. Everything is connected. I have stickers up here at the end that say graphs are everywhere, and you are all free to take them. So I'm sorry I poisoned your mind, because now you're not going to be able to walk around without seeing graphs everywhere. The other really neat thing about graphs is that they work the way that most developers think. I try not to make assumptions about the way that most people learn and process information, but I'm going to go ahead and bet that if you've done software development of any kind, you've probably used a whiteboard in some sense. You've probably drawn a big circle on the whiteboard and put a name on it like user. You've probably drawn a big arrow to another big circle or square that says document or page or, you know, truck or car or whatever it is your application's modeling. All those circles and arrows, that's a big graph. You just drew your graph on a whiteboard, and now you're going to sit down and try and take that beautiful graph on the whiteboard and break it down into tabular boxes. But when you were modeling your application, you didn't draw tabular boxes, you drew a graph. So why not use a data store that models your application data in the same way that you and your users think about it? Avoid having to do that big gray arrow of translation. So now we're going to get back to the Kevin Bacon game. So here's a big graph of actors and movies that they've been in. It's a small little portion of IMDb that I found. And now we want to say, okay, there's Keanu Reeves up there in the upper right, left. There's Kevin Bacon down there in the lower right. Find the path from Keanu Reeves to Kevin Bacon. Did it just kind of pop right out at you? You just follow it from actor to movie to actor to movie to actor? None of that weird select all the movies and then select the actors in them in big growing sets as the sets get larger and the degrees get larger. It's simply find me a path from an actor who's named Keanu Reeves to another actor who's named Kevin Bacon. I'm cheating a little bit here. We'll talk about why I'm cheating a little bit. But first I want to introduce you to the Cypher query language. The Cypher query language is a language that the Neo4j guys developed to make graph processing natural, make it look easy. So forget this match shortest path part, forget this where name is blah and name is blah, forget this return, and just look at this actor, some relationship to another actor. You can almost see the whiteboard behind that. I drew a big circle, named it Keanu Reeves. I drew an arrow to another circle, named it Kevin Bacon. The whole point of Cypher is to make those types of queries look the same way that you would actually model them or think about them. So let's actually look a little bit at what this looks like in real life. And I can't really see that well. So try and do this here. But this is the web interface to Neo4j. It comes standard with Neo4j 2.0. The old 1 point whatever version of the web interface was kind of crap. Nobody liked it. This one is much cooler. And I'm going to say match n. No, I'm not going to say that. Match n, return n. And what that means is match n, match all the nodes. N is just a variable. I could have called it A or whatever. But I haven't put any restrictions on what that node could be. So match N without any criteria is going to say, find all the nodes and return them.
So akin to select star from.
Yes, select star, except it's select star from every table.
Right, exactly.
And then I'm going to run that. Derp. And here's my graph. This graph actually covers a ton of different domains because I was going to kind of get in some different examples of doing cross-domain applications and things. But way down here, at this side, we have all of our movie nodes. So we have like The Matrix and Mystic River. And we have all of our actor nodes like Keanu Reeves and Lawrence Fishburne's in there and Kevin Bacon down there. Then we have some other nodes, these gray nodes in the middle, that represent me and my wife and some friends of ours who all watch movies. We have some other nodes that represent all of our houses. We have some other nodes that represent intersections between our houses in the fake little town that I've created for us. And we have all these relationships between these nodes. So we have actors pointing to movies where the relationship is an acted-in relationship. We have friend of relationships between the people nodes over there, or spouse relationships in case they're married. We have the lives at relationships between those people and the places that they live. And then we have the intersections that those houses are physically in the universe. So let's cut this down a little bit because that's kind of hard to see. And instead, we're going to say, find me only the actor nodes.
Return was typo.
I can't see from this angle. So,
Free.
thank you. TURN. Better? Awesome. So there's all my actors. No relationships, because I didn't actually ask for any of the relationships in this case. But this does give me a good opportunity to show you that the interface will show you what the nodes and relationships you have are, but you can also see them in a more tabular format. These are all the nodes I just selected. Let's change it up a little bit. Let's say match my actors. Hi. I'm going to spin around this way, if you don't mind.
You have a microphone, so we can still hear you.
Okay, good. Also, for some reason, Chrome keeps dying on me. Match all of my actors to all of the movies that they've been in. Hold on, oops. Find all the acted-in relationships to all the movies that they've been in. And then return the actor and the movie.
So the A and M are just variables you name?
They're just variables that you can name. I'm not going to go real deep into Cypher syntax because, again, the docs are really good. I just want to kind of demonstrate the sorts of things that are possible. So there's our tabular layout. We have all the actors and all the movies that they've been in. And there's our graph. Unfortunately, Chrome just died on me. So I'll have to bring my presentation back up. Or maybe not.
Oh, snap.
Oh, snap. Just do it. We'll just do it from here. So now, I have a couple saved queries over here. I'm going to go to. And that query we saw before about the shortest path between two nodes is somewhere in here. Shortest path between blah, blah. So, shortest path between some actor K, matching through some relationships. We don't really care what type of relationships they are. I didn't put an arrow on either end here because I don't really even care what the direction of the relationships are.
So you can specify direction?
You can specify direction,
Less than
so
or greater than?
exactly. pointing in the direction that you care about, to some other actor, and I want the first actor to be named Keanu Reeves, the second actor to be named Kevin Bacon. This shortest path function is how I was cheating before. It's going to return to me a path. In fact, it's going to find the shortest path between all the nodes, or if there's more than one, it's going to return all of them. Assign that set of paths to P, and then return those paths to me, and also return the length of the path divided by 2, because that's going to tell me how many degrees away from Kevin Bacon I am. The reason we're dividing it by 2 is because we don't want all the movies in between. We want an actor to a movie to be 1 degree. So what this looks like is that Keanu Reeves was in The Matrix with Lawrence Fishburne, who was in Mystic River with Kevin Bacon. Cool, we just played the Kevin Bacon game. The reason this is so cool is because it doesn't matter how long that path is. Kevin Bacon could have been 8 degrees away from Keanu Reeves. We didn't limit how long we wanted the path to be, so it doesn't actually matter how far away Kevin Bacon is. If there is a path between them, the graph database will find them, and it will find it much faster than an equivalent SQL query or set of SQL queries will do. The Neo4j guys, the CEO of Neo Technologies, Emil Ephraim, gave a presentation a couple of years ago where they had an unnamed social network come to them and ask them to find, given some users, all the users who are 4 degrees or less away from them. They ran this on a couple thousand users that all had an average of 50 relationships between each of them. The graph database that they came up with and the query that they came up with ran in something like 2 seconds across all these thousands of users. The equivalent SQL statement they came up with, they actually killed the process after 2 days. That's how long it was taking to find all those users.
Did they switch?
What's that?
Did they switch?
I do not know. They didn't actually name the social network, so it's hard to tell. Let me get my presentation back up here.
Neo4 is open source.
It comes in different flavors. The community edition is open source. And it comes with all the stuff I'm talking about here. The ones you have to pay for are basically buy you things like support from Neo Technologies. They buy you things like clustering ability and high availability, things like that, that aren't just the basic download this Java jar and run it type stuff. So anyway, so playing Kevin Bacon. So there's a social element to this graph as well, right? There's people who have watched movies. So in this case, what we're going to talk about is, what movie should we watch? And the answer to that question is the one that the fewest number of people have seen, right? We don't want everybody to be watching the movies that they've all watched before. So what we're going to do is we're going to find all the people who are my friends. So select me as a person, find all of my friends, and bind those friends' name to the variable p, and then select all the movies, and then add some additional criteria where there is not a path between that person watching that movie. So rather than say, we could also say where a person has watched a movie, but we want to find the movie that the fewest people have watched. That's going to give us the number, essentially a table, if you think about it, of all the people and all the movies that they haven't seen. Then we're going to group the people together by movie and count how many people have not seen every movie. Order it by the one that the most people haven't seen and return it. So again, this is just kind of showing off some of the types of things that Cypher can do. And I believe I have that query.
Cypher is specific to Neo4j.
It is specific to Neo4j. They're trying to standardize it a little bit more. Is that one? No, it's people who haven't seen a movie starring Kevin Bacon, actually. So that's people who haven't seen Mystic River. Somewhere in here. I have, there we go, that's it. So it turns out not a lot of people have seen Mystic River. That's probably the movie we want to watch. And then those other queries that I just kind of went through briefly looking for this one because I haven't figured out how to name queries in this interface yet, were basically just extensions of this. I could use this basic query and I could add additional things maybe onto the not has watched thing where I could say from movie acted in Kevin Bacon. And that would basically give me all the people who haven't seen a movie that stars Kevin Bacon.
Josh,
Yes?
what if you took off the limit 1 on there? What would the resultant data look like?
For this data set, it would probably look the same because it's not a very big data set. But for a larger data set, actually, that's not true. Let me take off the limit 1.
And does it just set the count as a property on that node?
No, it sets it as,
Probably a runtime variable.
yeah, okay, so this did return some people. So this is returning our set of results, and we can see that 3 of the people in the data set haven't seen Mystic River, and 2 of them haven't seen the movie Higher Learning, which is only in there because it has Lawrence Fishburne and Jennifer Connelly in it. It's a good movie if you've never seen it. I would recommend it.
2 people have.
So these are just some of the examples, and I'm going to run out of time if I try and go through a lot more examples. But there's other stuff in there. You saw I had the relationships between who's friends with who and who's married to who. I had the relationships between where all these people live. So for our movie night, I could say, now find me directions from someone's house to someone else's house. I could say, find the person who has seen the fewest movies and figure out directions from everybody's house to that person's house so that we can have a giant movie watching party to get them up to speed. And all this stuff is possible by just describing what the graphs look like, what I want some node to look like, some relationship to some other node, and they're doing various types of pattern matching. There's so much more involved in this stuff that I just don't have time to get into. I said I cut this down from 1:45, and I did it by getting rid of a lot of this stuff. Mutating Cipher, so basically doing inserts and updates, which are kind of equivalent to create and merge, but have some really useful things. So for instance, you can say create unique. So create unique a node named Josh. If there isn't a node named Josh already in the system, it will create it and return it to me. Otherwise, it'll just return the existing node named Josh. Create a node named Josh that has a married to relationship to a node named Tara. If the node named Josh already exists, but the married to relationship doesn't exist and the Tara entity node doesn't exist, it will create basically only the parts that it needs to fill in that relationship. If both Josh and Tara are already in the system, it'll just create the married to relationship. So really cool stuff that you can do that would be slightly more difficult to do in something like SQL, where you'd have to either search for the things beforehand or try and create it in a unique way and wait for it to fail because you just violated some constraint somewhere. Indexing on the various node properties. Auto-indexing, so every time I create a node that has an age property or a height property or a name property, index on that so that I can speed up my query to find it. Full text, so this is all driven behind the scenes by the Lucene query engine. So you can use Lucene syntax directly inside of Cypher to do querying. Spatial indexing, if you provide latitude and longitude on a node and then you create basically layers and explain how nodes are spaced out amongst each other.
So you can define the distances between nodes.
Yeah, except you don't have to explicit.
Coordinates,
Yeah, you just say the coordinates, and then if you have the spatial index plugin installed, it'll do those calculations. And you can do things like haversine distance, bounding box queries, all that sort of stuff. Batches and transactions. Neo4j made a decision early on that they were not going to drop ACID compliance just to get performance gains. These are guys who work with data sets. Some of their customers have data sets that are in billions of nodes and relationships. And those customers are working in things like banking or medicine or other things where it's really important that when the database says something is on disk, it's actually on disk. So they have transactionality built right into the database. And then you can run it embedded, so if you're writing a Java application, or you're writing an application that runs on the JVM, so JRuby or Jython or Clojure or something like that, you can embed Neo4j directly in your application. For the rest of us, there's a REST interface. It's basically just posts and puts and gets and all the things that you normally expect from a REST interface. So now that we know everything can be modeled as a graph, why would you ever possibly want to use a relational database? Well, because it turns out there are things that relational databases are actually good at. Basically, anything dealing with actual set math, a relational database is really good at. Things like aggregation. Find me the minimum or maximum of some set of values. It's really easy for a relational database because it already has the set of all those values. For a graph database, it's a little harder because it has to go and find every single node and do the aggregation over all those nodes. Now that nodes can have labels on them, it actually makes it a little easier because you can use labels almost like table names and just say you have a specific set of nodes. Ordering data, same thing. It has to find all of them before it can order them. Or things that just don't have a lot of relationships. If you have a stack of data that isn't related to any other data, you might not have any relationships between them, in which case relational database is probably going to be a little easier for you to use than a relational database. So the Neo4j guys like to say that a relational database will tell you the salary of everybody in this room, but a graph database will tell you who in this room will buy you a beer. So this is my graph to explain how graphs work. So graphs use indexes to organize nodes and relationships. Traversers like Cypher find relationships in nodes. Relationships in nodes have properties. Relationships relate nodes. This is basically the property graph represented as a graph. And I would be happy to answer any questions. Before I do, I just want to mention I was at Graph Connect in San Francisco a couple months ago, which is the big graph database conference, or one of the ones that the Neo4j guys actually put on. And they heard I was going to be here, and they gave me books. They gave me books. They gave me stickers. I know everyone's slavering over the books now, okay. So rather than it being kind of a first come, first serve, because I know everybody wants the books and the free swag, we're going to do this where I arbitrarily pick who I think asks the best questions. Remember, it's got to be a good one. Yes?
So I can see how the graph would be a lot faster than a relational database when there is a path. What are the performance drawbacks when there's not a path?
Sure.
To be found?
Sure. They're actually very similar because graph traversal algorithms have been around forever. They're one of the graph theory is one of the fundamental concepts of computer science, and they basically, if you start at so the way it works under the covers, and you can actually read about this in the book, you just won yourself by being the first person to ask a question.
Oh, did first come, first serve. He lied.
Just for the first one, though. Rather than starting at a node and kind of following the relationships out from there, they do some optimizations. They actually start traversing at both nodes and go out and wait until they intersect or not. The query I did before where I just said star, which means follow all the relationships forever, that's actually a really non-performant query. If you did have hundreds and thousands, or even just a couple tens of thousands of relationships between those two nodes, you're not doing any limiting factor. It's going to take a while to traverse those all. Still less than a relational database would to do the 10,000 joins. But it's going to take a while to do that. So there's actually, in Cypher, you can tell it, only traverse out this far. So only follow 12 relationships deep before you determine there's nothing there. And so what will happen under the covers is it will start at both nodes, traverse out 6 relationships deep from each of those nodes, and wait until it finds a common node. So, and if it can't find a common node, it'll just say there's no path here. There might be one at 13, but you told it, for performance reasons, limit it to a specific thing. Turns out, in most use cases, you don't have to go hundreds and hundreds of relationships deep. Yes?
Is there like a best practice for the threshold at which point you'd want to say, yes, I need to switch from trying to fake it with a relational database and moving towards a graph database?
The threshold is, I'm going to answer that question in 2 parts. The first part may negate your entire question, so we'll see.
Okay. Will we need a second part if you do the first part?
One of the neat things about just databases in general is your application doesn't need to have just one of them, right? They call it polyglot persistence. So you can use a relational database to store the things that are tabular, and a graph database to store the things that are graph-shaped, and use like primary keys or some common key between them, and just update both of them at the same time, and use the relational database to query for the things that you want to query in a relational aggregative way, and a graph database for things you want to query in more of a traversal path-based way.
So it hooks into MySQL?
It doesn't,
Not directly.
not
You
directly.
just store like the pointer in the graph database to.
Your application will still have to link this.
Right, your application, you'd still have to do something at the application layer that would say this row in the database has the same ID as this graph over here. I am not a Java person, but I've heard that there are Java database layers that can do cross-database transactionality. And those can give you some sort of, like, it has to be persisted here and persisted here in order for the transaction to be successful in both databases. I don't know anything about that. That's just rumors and hearsay to me. You might get a book. You'll definitely get a sticker. Everyone gets stickers. Yes?
Here's one thing that I haven't quite grasped yet, and hopefully this will answer. You talked about these nodes and the relation between them, okay? And I'm coming from the MySQL world where you're pretty much unlimited on how much data you can actually store. So if you have a row of data, then you've got multiple columns and you've got, you know, all of these things inside. Is there a way that you, if you say, for example, a person is a node, well then that person, would you also be able to say first name, last name? You know what I'm saying? I mean, is it first name, last name, address, da, 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 on the node? Or is that a separate node with a relation between them?
Sure. So the question is, and I was told to repeat the question for the mic. The question is, when do you know whether you should store a property on a node or relationship itself versus breaking it out into its own node?
Well, and can you have a multi-level node, if that makes sense? Can you treat a node like you would a row with multiple columns?
You can. So you can have
property hash,
right. Properties are basically a dictionary.
Oh,
So you can
okay.
have, it's a hash. You can have as many keys as you want. At the moment, and this may have changed in the most recent version, but I'd have to check. You can store scalar values only, so strings, booleans, and integers, and floats and things in your hash. You can have different things. You can have like a name that's a string and an age that's an integer,
But
or
it can
something
all
like
be on
that.
the same
It can be
node.
binary.
But they can all be the same. They can all be on the same node.
Okay.
The deeper question there is, are there in that set of data things that should be their own nodes? So for instance, you talked about the address.
Yeah.
Well, one node that's a person could have their address built directly into them as properties, but more than likely that address actually exists as a separate entity that maybe more than one person could live at.
So maybe the decision would be, if something could be, for in a relational sense, a one-to-many, then
It
that
should be its own
many should
entity.
exist as a node for others to also be
Yes.
able to relate to.
Sure.
Oh, okay. That
Even
makes
if
a lot
it's
more sense.
even if it's one-to-one.
Yeah.
Like if you have an entity that really is it's related to another entity, but it isn't part of what makes up that entity. So it really it would be the same as denormalizing your relational database, right? Rather than putting the addresses in each row, you might have a separate table of just addresses with keys and things. It's the same concept. If entities are more compositional rather than kind of intrinsic to themselves, break them out into their own nodes. Neo4j can store, I think, 32 billion nodes and 64 billion relationships, and I forget what the count of properties on each of those is, but the basic idea there is nodes and relationships are cheap. They're easy to make, and you can have as many of them as you want. A node can have many relationships, even to the same entity. So if an entity can actually be broken out into its own node, go ahead and do it, because you're storing the data as it actually exists in the real world. You're modeling it the same way it exists in the real world. You can denormalize much easier than you can with a relational database.
So, not to monopolize, but this is all like making sense, which is cool. So if you have a person and you have a city, then you could have two relations that say they were born in that city and they still live in that city.
Yes, precisely.
Okay.
You got a book for that. That was awesome. Someone pass that back to him.
Gives a light on.
Yes, I love epiphanies.
Thank you.
That was a really awesome example.
Makes sense now.
The lights have come on. Everything is connected. Yes.
So the database, I mean, I love this idea, and to be completely honest, when I thought of graph databases, I'm not particularly fond of a lot of things Facebook does, and I just thought it was a gimmick that they were putting on graph databases. I didn't understand it. I love it, but when it runs on the server, is this all in memory? Are these persisted to disk? How does that work in the back end? Because as I go to my team, they're going to have all these questions
Sure.
that we talk about, and then clustering, it sounds like it's a paid-for-only type of a thing. when you talk about
Absolutely.
availability.
The question was, how does this kind of work on disk? Like, what makes the storage and persistence of these things much different than a relational database? If I decide to bestow a book upon you, there's an entire section in the book that talks about the back end of this and how it is on disk. But at a very high level, the difference is in a relational database, you're basically storing, especially if you're using indexing, a giant tree, a giant B tree that you have to kind of follow down to say, okay, here's the index. And at that point, you have a pointer at a leaf node on that index that points to another place in memory that says, there's that thing. With a graph database, all those pointers are stored directly kind of with the node itself. So a node has intrinsic to it in its memory position a list of all the pointers to all of its relationships.
Oh.
And it'll go to those relationships, and those relationships have two pointers, one to their start node and one to their end node. So you're not following a tree that then indirectly tells you where another relation
getting directions.
is. It's a memory position to memory position to memory position thing. There's a technical term for that. I believe the technical term is called index-free adjacency. I could be wrong about that. I may have to look it up.
Cool.
Yeah, it sounds awesome, but it may not. Maybe a thing I just made up. But I did hear it from somewhere. I'm not smart enough to make up an awesome phrase like that myself. So, yes.
I have a question about the relationships. Is there a way to give them, or is it even necessary to have them have a cost? Like, is some relationship more expensive than another? Does that make sense?
Yes, it absolutely does.
The direction.
Wait, so you mean like the direction or like the traversal cost? Like,
Traversal.
so like for a map.
It's more of an abstract relationship.
Right, so like for a map, maybe the distance of how far it is down that road is the cost to traverse that, or for a network connection, how slow the bandwidth is, or things like that. So the question is, are all relationships weighted the same? Do they all have the same cost to traverse? And the answer is, you can decide that. You can actually put a property, so remember, a relationship can have properties just like a node can. A relationship is nothing more than a special type of node that has a start and an end to it. You can put a property on the relationship called cost, or distance, or weight, or something like that, and then you can use specific graph algorithms that use that property to determine basically the cost of traversal. And rather than saying, find me the shortest path, which treats all relationships as a unit of one, so the shortest path between three nodes is two relationships. If one of those relationships has a cost property that you've defined, and you tell the graph traverser, use that cost, and use like the Dijkstra algorithm or A star or something like that that takes cost into account, then you might have a shortest path that is a longer number of relationships, but the total cost of all those relationships is different than one that has fewer relationships with a higher cost. And you can determine that at an application level based on the properties that you've set on the relationship.
And then based on the query you've written.
And then based on the query you've written.
How does it know which kind of algorithm to use?
You can tell it.
Oh, you can tell them?
Yeah.
Does it choose automatically too or not?
With just basic Cypher, it treats all relationships the same. I'm not sure what the syntax is for using the different algorithms. Cypher's not the only way to traverse a graph in Neo4j. It's just the easiest one and the easiest one to understand. They also have other types of graph traversal mechanisms that are much lower level, where you can tell it things like use a star or use Dijkstra or use something like that. But at just a very high level, every relationship is just assumed to be a unit of one, a unit cost of one, unless you tell it otherwise. Yes, you don't get another
I
button.
know, I don't want one. I'm smarting here. So if the company I work for, we basically map students to the best school that we can find for them.
Okay.
So I'm just going, oh, this is awesome, because would I be able to have something that says, here's a student who lives here, wants to study this, and is this age, and here's a school who offers this, it's located here, that wants students of this age. So you could do multi-relationships to find the best match. It's not a singular, it's not
No.
like,
So we saw before I had that match clause that said match actor to movie to actor,
which was one path.
which was one path. You could have another path as well that says match that first one and this second one and a third and a fourth, and all those paths might be not related to each other. Like the only
Well, it'll
relationship.
come back with the best combo.
Right, it'll find the thing that matches all of the things you told it to match. So you can match on multiple.
Can you do ands or ors on those matches, or do you know?
There's a way to do optional matches.
Oh.
I don't know if you can do things like XOR. You
Right.
might be able to do things like XOR, but you can definitely do optional matches. So say match this path and optionally this other path, and in your return set of results, it'll tell you.
Ordered by, yeah.
Right. It'll tell you here's the path that I found, and then I did or I didn't find this other path as well.
Would it be super good for scheduling?
For scheduling,
Yeah.
I maybe. It depends kind of how you define your domain. Yes.
So do you, with a MySQL database, you're monitoring it and watching for slow queries and things like that. Do you have to do things like that with Neo4j graph? Or?
Yeah. I mean that's so the question there was, do you have to do things like monitoring for performance? And I would also throw in things like resource usage, query optimization, things like that. That's just basic database administration stuff, right? You don't get away from doing database administration when you get away from relational databases.
Some kind of explain or indexes for whatever reason.
Yeah,
Or
that's.
Oh, can you do like explain
What
and
kind of
stuff like
tools
that?
does it give
Yeah.
you?
I'm not actually sure. That's a really good
It
question.
doesn't need it, it's just so
Oh,
fast.
So,
No,
so
that's-
how long has it been being used for? I mean, because you're gonna have another guy that's a different guy, right? Your DBA is not probably gonna be able to do this.
Yeah, if your DBA is just trained in relational databases like MySQL or SQL Server or Oracle or something, yeah, I mean it's a different tool set. Neo4j's actually been around for about 11 years now. They started way back in like 2000 or 2001. So actually it's probably more than that. I don't remember exactly. It's been around for a while. Like most of the other NoSQL solutions, the idea of a graph database or a document database or a column store database have been around for a really long time. It's just they're not the thing that gained wide acceptance. So basically, you'd have the same issue finding someone who knows graph databases really well as you would finding someone who knows, say, like Cassandra really well or MongoDB really well. It's another NoSQL database. It's a totally different skill set from administrating a MySQL server.
All right, so how big is the community, and are there others? Are there others that have bigger communities or more support? Or is this-
There's not another graph database that has a bigger community
Okay.
than Neo4j. Neo4j is the oldest of kind of the major graph database vendors. There's some other graph databases out there. So Infinigraph is another one. OrientDB is another graph. I'm not really sure how big their communities are. I know they're out there. I know they have those communities, and there are companies that are using those graphs to great success. I'm not as familiar with them. But Neo4j has, I mean, just from a company standpoint, Neo Technology, their team is amazing. And as far as kind of just community out there using this, their support forums are really active. Stack Overflow is really active. You can see people getting answers to graph questions in like minutes. I mean, it's active. You're not going to be left in the dark if you have questions. You're not just going to be kind of left hanging. But like any other technology that you're thinking about incorporating into your product, you definitely want to do your research into that kind of thing before you decide to go whole hog in it. You want to make sure you're going to get the support that you need either from the community or professionally from Neo. One more question. Anyone else? Anyone else? Sorry. It's a really awesome book, though. Let me hold it up so that everyone can see. All right. It's an old Riley book with an octopus on it. It's called Graph Databases. It's actually by Emil Ephraim and Jim Weber and Ian Robinson, who are the grand high poobahs of graphness at Neo4j. So just, again, I want to thank y'all for being here. If you're interested in using Neo4j from PHP, please check out Neo4j PHP. Send me feedback on that stuff. Neo4j.org is your starting place for getting started with Neo4j. The docs, like I said, are amazing. They're really awesome. They have a Google group. They have Stack Overflow, really, really good resources. Jim Weber is the chief scientist at Neo Technologies. He's a hilarious guy. I mean, he's actually Dr. Jim Weber. But I mean, he's just funny. He's awesome to listen to. He's British, so everything he says sounds really like Monty Pythonish. He gives a talk over and over again at different conferences called A Little Graph Theory for the Busy Developer. I suggest you watch it. He talks about things like Doctor Who and World War II and various other things like that. It's really hilarious. That's a way to get to my blog, joshadell.com. And again, I would really love to get feedback on this. So please check out Joined In, give me feedback, rate the talk, and let me know what you liked and didn't like. And I appreciate your time. Thank you.